Great. Well, let me start actually asking you all guys a question. How do you know if your data set is complete? That's what we're going to talk about today. So I'm Martin. I work at Uber. I'm working as an engineer on the storage platform team. And today we're going to talk about this thing we built called Ledger Store, which is using DynamoDB under the hood. So what are we going to be talking about? First, I'm going to give you a bit of background to what is it we're actually trying to solve. A little bit of what is Uber, in case you don't know. Then Uber Ledger Store, which is the thing we actually build on top of DynamoDB and some other Amazon technologies. Then I'm going to deep dive on two specific components of our system. One is time-ordered indexes, and the other one is completeness. So this is the how do you know whether your data is actually complete. So let's start with some background. So what is Uber? I assume everyone knows, but just for context, it's this transportation platform where you can request a ride and you partner up, or it matches you up with a driver partner and then drives you to wherever you need to go. So just to give you a little bit of context of what is Uber and the kind of scale, because these numbers kind of get important later on when we kind of talk about what is the kind of scale and volume we actually running this system in. So we have more than 15 million trips per day and across 16 countries. So what this means is that every second, thousands of trips are happening. So our system has to handle quite a bit of volume to kind of track how transactions are actually happening in the system. So just to give you a very quick overview of how a trip works. So basically we have these two systems. We have a marketplace and we have a post-processing. So what happens if a rider opens their app and they want to go from their home to work? So they type in saying, I want to go to some destination. At the same time, there's a lot of these driver partners that's connected to the marketplace. And we basically match up the rider and the driver to kind of find the best match so that it's where they are, they're going the right direction, and so on. So when that happens, we create a trip. And for the lifetime of that trip, basically from you get into the car and to you get out and everything's done, it lives in the marketplace. So it keeps track of all the states and GPS coordinates and all this stuff. When that's done, it moves into post-processing. And in post-processing, a lot of stuff is happening, like fraud detection and all that kind of stuff, but also a lot of payments is happening. So that is, make sure that the rider's credit card is charged, that we pay out money to the driver, and if you're tipping, then make sure that the driver gets the tip, and so on. So generally, there's a lot of money processing going on in here. And with 15 million trips a day, that's actually translated into hundreds of millions of transactions with money moving back and forth between accounts. So, and that's what we're basically going to talk about today. It is how do we make a digital version of this basically ledger of accounts. So if anyone knows what a ledger is, it's kind of the old style book like this, where you write in saying I'm moving money from account A to account B, and then you write that on both accounts. A ledger has to put the property that it's immutable, it's append only, so you can't change it once you put it in. The only way you make a change is to just say, well, I'm going to move the money back from this account. So basically, we're building an append-only data store to kind of follow the ledger semantics. So building any kind of ledger that just basically need to receive a lot of writes, and yeah, that's fairly easy to do at scale because you can just write it, and you can use DynamoDB, for example, that horizontal scalable, and you can easily just dump a lot of data in there. But when you're building a database, the reason why you're building is most likely because the data has value, so you want to read it again. So one of the main use case for this kind of money transactions is that we want to be able to generate reports of what's going on in our system. So for example, we want to say, what was all the trips, how many trips happened in month of May 2019 in this city? So it's really centered around this time-ordered queries where we want to generate reports of something. So in the simple case, this will basically be it, that you have a ledger, you do a read, and you generate your report. But in reality, when you're building at the size we are, it actually looks more like this. So you have a bunch of steps where you're processing your data, and you're aggregating, you're having derivatives, and so on, and you generate a lot of different reports. But now that the question kind of comes, how do we know if any of these steps have bugs? What if some of them is losing data? So what if this one actually had a bug that, for some reason, it just suddenly dropped 1 out of 100,000 records? How would the subsequent report generators actually know that there was a problem here? And that's basically what we're trying to solve with this ledger store system. So to give a quick sense of what it is, Basically what we do is we introduce signed resources that we basically propagate through the system. So each step can basically propagate saying this is what the data I get in, this is my output data, and you can validate all along the way about what is the data and is it actually complete. Because if you go back to this one, even if I knew that there was a problem here, how would I even validate that? Because what is the exact number that this guy should be compared to? Is it what the first one generates, or is it back in the ledger? That kind of requires you to know a bit about what the first step does. So it's actually quite difficult to figure out what is the correct value we're looking for, because what is the expected count of this data? And how do you know that some data haven't been changed on the way? Like if there's a bit flip or something and the data has been being changed compared to what you expected. So what we're looking at with Ledger Store is how do we do these signed resources, and how do we establish the root signed resources, which is the Ledger Store. So that's what we're going to be talking about today. And this is where Uber Ledger Store kind of comes in. Uber Ledger Store is a service we built and are running at Uber's data centers that using DynamoDB underneath. And this is the kind of the interface that all our users talk to. So they don't talk directly to DynamoDB, they talk to the Ledger Store. So what kind of requirements do we actually have for a system like this? So some of these are pretty normal. So for example, we want strongly consistent writes, but we also want strongly consistent indexes. And if anyone you worked with DynamoDB before, you know they don't provide strongly consistent global indexes out of the box. They have local indexes, but not global, which is what we want. We want to have support for time-ordered indexes, so we can generate the reports I was talking about. And we want to have this verifiable, immutable time range queries, which I'm going to get into a little bit more later. But basically that is, if I do a query for the month of May 2019, I want to be damn sure that when I do the same query in 5 years, I get exactly the same result. And if I don't, then I'll know why that was changed. So we want to have complete tracking of what happened. And this is even if the database underneath somehow lost data or whatever it might be, we want to be absolutely sure that we generate the same kind of results. Obviously, this is for compliance because we're tracking a lot of money movements here. And the last kind of requirements we have is we need to be able to support both online and batch workflows. So as you saw in the beginning, we have the marketplaces kind of writing the trip when it's done. So we need to have something that can handle these live requests, so at low latency and high volume. But at the same time, we also need a system that can actually read this out, like a full month of transactions. That's millions of records we need to read. And we need to be able to have something that can handle that with a very high throughput, and something that at the same time is this verifiable. So there's kind of two competing aspects here of the requirements. So let's look a little bit about what we actually did. So the basic idea is this. You have a user, we have this unified query language, which we use internally at Uber, that talks to Ledger Store. This unified query language is like SQL-like thing, where basically you can insert and select and so on. Ledger Store talks to DynamoDB, which is running in 2 regions. We're running with a primary and a secondary region, so we can do disaster recovery in case the first region fails, but also because we can actually increase our read throughput when we have basically our Ledger Store is distributed around the world. So the reason why we chose DynamoDB is because it's really good for this high throughput use case, and it has support for range queries, and it has support for global tables, which is async replication between regions. So DynamoDB does have strong consistency, meaning that I can write a record, and I know that I can't have 2 conflicting writes, and there's inconsistency in which one actually wins. So a write is atomic, meaning we have the kind of property we need in terms of our primary key constraint. But we don't have strongly consistent indexes out of the box. So that's one of the things that we're then building in Ledger Store to have a strong, consistent secondary index, a global secondary index. Also, we need strong consistency in between regions, because we want to make sure that if I serve a read from a secondary region, I need to make sure that's exactly right. For example, that this query I did previously in region A has to produce the same thing as when I do it in region B. But with eventual consistency, that's a little bit tricky because there can be delays. There can be all kinds of things happening because it's not part of the initial transaction. But luckily, we are able to kind of relax our requirement here and let Ledger Store kind of route the traffic based on where we know the system is consistent. So this is why we have this dotted arrow here, is because Ledger Store can actually read from both when it has a certain knowledge about it. So DynamoDB is great for these high volume write use cases, and it has range queries, which is great for really pushing down the queries down to the storage layer. But we have an append-only system, and with the volume we're generating, it actually grows quite fast. And DynamoDB, it does cost a bit of money when you're reaching the terabyte scale of storing data. And most of the data, in our case, we're actually only reading very rarely. So what we did instead is we actually used another technology, which is S3. So we move stuff, basically the cold stuff, from the DynamoDB and move it over to S3. And we basically order in a way so that we can stream directly from S3 through Ledger Store out to the client, because we put it in the time order that the client wants to query in. That means that now, instead of having to do a lot of queries and pulling down to DynamoDB, we can actually now just pull out from the S3, and then we're limited by the throughput S3 can give, which is much higher in bytes than we can achieve from DynamoDB. So this way, we basically balance price, but we also make sure that we take advantage of the two systems and take advantage of what they actually built for. Great. So now let's dive a little bit into how we're actually doing this, this consistent indexing. So this basically, this is going to be used throughout the slides. But for now, I'm just going to explain how we do it, and then for the subsequent slides, I'm just going to leave this out. But basically, I'm going to tell you how we're doing these consistent indexes. So what we do is we have two independent DynamoDB tables. So it's not a DynamoDB index, it's just two different tables that we manage. So what we do is the first thing happens is you insert an intent into the index table. If you're familiar with two-phase commit, this will be very similar to what you know. So we insert an intent, and intent basically means we intend to write this, but it's not committed yet. And this can see with the last thing here where it says intent yes. Then we go ahead and write to the record table, and when that's done, we consider the thing committed, and now any read would be able to read the record both on the index table and the record table. If I did a read right now at the index table, I'll say, well, that's an intent. Let me just go and check whether the record is there. If it is, I'll return it. If not, I'll ignore it. So that's basically how it is, and then the next thing that happens is you change the intent to no, and then everything is done. So here everyone is happy, but obviously that's the case. What happens when there's two concurrent writers that want to write the same key at the same time? We want to make sure that only one of them wins, and the index is correct in that case. And this is what this checksum here is about. So if you see, we have a checksum on the record table, and that's also on the index table as part of the primary key. So what we do in a concurrent case is that we have two guys, two services trying to write with the same record key, but different index key. And as you can see, they have different checksums as well. Both of them are intent. So far, you can't read anything. One of them is now going to write to the record table. And here we take advantage of the fact that write to DynamoDB is atomic, and we can use a conditional expression. So basically say, insert this if it doesn't exist, which means one of them is going to win. The winner now goes in and marks its own row as being committed, so the intent is changed to no, and the loser goes out and actually moves the index row. And now we actually be able to resolve these concurrent writes. So that's very short. That's how our strongly consistent indexing actually works. So now I'm going to kind of build on top of that and talk about how we then handle a special case of time-ordered indexes. And time-ordered index has a bit of a challenge, and this is a challenge that exists for all kind of distributed system or partition system. This is not unique to DynamoDB. Any partition system will have this kind of problem. So, in case you don't know, so this is kind of the problem with having time series. If we created a table like this, where we basically have a partition key that's just on this P key, and we took in a record and we just rounded down to the nearest hour. What will happen then? Well, the Ledger Store would actually start writing to the same partition key because we want to kind of group all the data together so we can take advantage of the fact we do range queries on a particular time range. So what's going to happen is that during the same time period, so everyone is writing at the same time, the transaction is happening at the same time, so they'll all start writing to the same underlying partition, the same partition key, which means we're now going to be throttled by what a single partition in DynamoDB can handle, meaning that even if we wanted to go above that, well, if we wanted to go above that volume, we're just going to get throttled and we can't go beyond that. And that's just not enough for our use case. And if we continue over time, this will just continue, so nothing is ever going to be better. It's just going to continue to hit this hotshot problem. So how do we then go about solving that? So we chose an option where we call it two-stage indexing. So the first thing that happens is that every day we create a buffer table. A buffer table is just a normal table as anything else in DynamoDB, except we change the partitioning key a bit when we actually write to it. So what we do is we take the record key modulus with n, which is just a variable here, for example, 32, 64, whatever, that kind of fits the use case, and we basically shard the data among multiple partition keys in DynamoDB. So this means we can take now advantage of n different partition keys instead of one, while still being, so that means we can now get the write volume that we actually want. However, this is not great for reads, because if I have to do a read now, I have to do a fan-out query to n different partitions, and I have to merge them, and I have to do all kinds of stuff, meaning it's now harder and more expensive to do any kind of reads in this. So that's where the kind of the two-stage come in. So then we have a long-term table, which is also a DynamoDB table, where we actually keep our data for the long term. So this is where we keep our index data for the duration of whatever this use case is. And we use Spark to kind of offload that. So when the day is over, we shift the traffic to a new table, and we start a Spark job that kind of moves it over. But here you may ask, wouldn't this Spark job then hit the same problems as before, where we just start hitting this partitioning key? But here the trick is that we actually can do this in parallel, so we can write to all, in this case, 24 partition keys in parallel, meaning we can have 24,000 VCUs compared to 1,000 VCUs before, which is at least the current limits on a single partition key. But you may also ask, why don't we just keep these buffer tables around forever? Because we can just keep adding them, and we don't have to move them, and we'll save the cost there. The main problem is, well, for the first thing, it's hard to read, because you have to do these fan-out queries. And the other thing is, there's actually a limit how many tables you can have into your account and how many you actually want to manage. So moving them into a long-term table means we can basically group things together in the data locality where they belong, meaning we can do more efficient queries here. Because when we then take advantage of range queries in DynamoDB, we can now push that down to DynamoDB instead of having to do all of that up in Register. Great. Another advantage of this is that we can now actually adjust how our write volume and read volume should be, or Spark write volume as well. So here, if we increase n, that means we can now have a bigger sustained throughput on the right side, but it also means it makes it harder to read it. So obviously that's a trade-off. And in terms of the long-term table, the smaller partitions you make, the more throughput the Spark job can do, but it also means that if you're doing very sparse indexing, doing a query where it only returns a very sparse result, then it's going to be more expensive because you have to do more queries. So that's kind of the trade-off we kind of have to manage. And we can manage these variables live in our system. Great. So this Spark job, how does that work? So we call it index offloading, and luckily this is very simple because DynamoDB actually provides the Spark connector out of the box. And this is the whole code right here. This is actually code from our system, just moved some comments. This is all it takes to actually move the data from one table, reshuffle it, and move it into another. And so this is all the things it does. If anyone knows Spark, yeah, you'll see that that's fairly straightforward. One of the things that you kind of have to handle with this case is that the Spark connector, when it starts up, it goes in and asks how much capacity does this table has. And then it takes some percentage of that capacity, and then it uses that statically throughout the job. Which means that if you have very low read capacity allocated when you start the job, your job is going to be slow because it's not going to basically make it scale. So what we do instead is we actually do pre-scaling in this, where before we start the job, we add a lot of capacity, we start the job, and now it takes that capacity for the offloading. And then afterwards, we can dial it down again. Okay, so that might sound fairly straightforward, like we create a table, we offload it, and delete the table, and then we're done. But there's actually quite a few steps involved here because we have to manage this capacity and because we're running in multiple regions, as we saw before. So we basically have to build this table lifecycle where a single buffer table gonna move through this simple model. So the first thing that happens is a table is in its new state. That usually happens 2 or 3 hours before midnight when we do the change, because we want to have time to actually go in and create these tables in DynamoDB. So we move it into created when the table is created in all regions and we set up replication. So that's a multi-step process where we basically go in and create the tables in all the regions, we set up replication, everything is happy. The next thing we want to do is we want to make it ready. And we do that by basically pre-splitting the table. So when I create a new table, it's allocating a certain number of partitions, which are not that high. But we know that we're going to actually hit this with quite a bit of volume. So we want to make sure that it's primed and ready to actually receive these writes. So what we do is we pre-split it by allocating the predicted capacity. We wait for it to scale up, and when that's done, we scale it down again. So basically now we move it down to just the minimum capacity, so it's ready to be used at midnight. When midnight comes, we close the other table and we open this one. And when we open it, we increase the capacity again, so it's now ready to actually receive these writes. So the day passes, and then at midnight, we move it into closed state. And here we decrease the capacity and make it ready for basically doing this offloading. But we don't want to pay for all the write volume while we're offloading, because we're not going to be using it. So the offload job gets kicked off, and when we do that, we increase the read capacity, and we start the index offloading, which is just the Spark job I showed earlier. When it's offloaded, we do some validation, and then we actually mark the table as being deleted, meaning that the data in there, we're not going to use it anymore, and all reads are now going to the long-term table instead. After a bit of quarantine, we go in and delete the table physically. And the reason why we're deleting the table is because it's cheaper to delete the table and create a new one than going in and individually delete these millions of items, because you have to pay per item. So we opted for actually going in and delete the table instead. Great. So, maybe I say this a lot, but while that seems simple, there was obviously a few challenges with doing this. So Ledger is a multi-tenant system where we have a lot of different stakeholders using it at the same time, and they all create tables and indexes and so on. So we kind of have to manage all these different tables. So in that there was presented a few limits, few challenges. So while the DynamoDB management API is excellent, you can do everything you want, you can see everything you need, there's still some limits we kind of have to work around. So one of them is that there's a limit on how many table arrays requests you can do. So for example, describe table, create table, and so on. There's a limit of how many requests of them you can do per second. There's also a limit of how many concurrent table operations can you have ongoing at any given time per account. Meaning that if I create a table, it actually kicks off a background task that creates partitions, sets everything up, and completes at some point. And there's a limit to how many can you actually have of these. Further, we have this thing where we actually do global tables, so we have to create tables in multiple regions, and then we set up the global table. That requires multiple API calls to kind of set that up. And at least before, when we built this, replication had to be done on an empty table, but now with the new replication protocol, that's no longer a requirement. But it's still a multi-step process that had to be done. So the solution we opted for here was a goal state-based table manager. So we have one table manager that takes the input from all the different stakeholders and continuously sits around and makes sure all the tables are in the right state. And it does this by basically shifting around, looking at the different tables, and spreading out that limited on the number of requests you have around these different tables. So all of them is making progress, and in the end, it converges against what we actually want. At least for us, we didn't expect this when we started, but now that we have it, it's become very simple for us to kind of manage all these tables, because it's just set up a goal of, I want this table, and then everything is going to be taken care of. Great. So that was time-ordered indexes. So that is, how do we being able to write this to an index and put it in a way so we can actually read it again, so we can serve these queries that we talked about in the beginning. The other big feature we talk about is this completeness. So that is, how can I verify that when I'm querying from this data store, that I'm getting all of it, so that nothing was dropped in the query layer, that the database didn't lose something, or that whatever it could be. How do I ensure that all my data is there? And the way we kind of like to talk about this is illustrated with a haystack. So everyone kind of knows the find needle in the haystack, and that's kind of an analogy we're going for here. We're changing it a little bit, so basically it says, it's a piece of the straw missing from the haystack. So that's kind of correspond to, is some of the data missing? But for our case, we want to take it a bit further. So we're not just going to say if something is missing. We also want to say, is there something in there that's not supposed to be there? So if someone managed to get access to our keys and insert data that says they should have $1 million back, we want to be able to see that we wrote that, not someone malicious. And if we take it a bit further, we also want to see, has any straw been bent in the haystack? So that is, has any data been changed compared to what we actually expected? So we don't want anyone to go in and change values and all of a sudden they need to get paid out a lot of extra money. We want to know exactly that what we put in is there and it can't be changed as when it's being accepted by the system. So if you look at how that actually works and why that might be a problem, is that, so we have the stakeholder talking to Ledger Store. and they write to DynamoDB, which is the record table and index table. So here in this case, the index table is these two tables with the two-phase commit and buffer tables and so on. But for illustration purpose, I'm just going to use a single table here. But the idea is the same. So already here, you could actually have a problem, because what if there was a bug in the indexing system that somehow it missed a record? So already here, there can actually be a problem with the system. And it gets even worse when we're now starting to do replication, because now we have two regions, there's two DynamoDB tables, and they're independently replicated. So what if there's the replication delay on the index table but not on the record table, or the other way around? How do we make sure that when I read from the secondary region, that I'm actually seeing the full picture? I'm not seeing a subset of an index because they haven't been replicated yet. So that's kind of the problem we're going for here, that we want to be able to solve this particular case where we have eventually consistent replication, but we want to have strong consistency on our reads. The way we went for this is we say we're willing to trade availability for consistency here. So on our writes, we want to have that it's highly available, we can always write the thing. But on reads, we're willing to wait a bit to make sure that what we're getting is the complete picture. We don't want any partial results when we're building this, or when you're running this. So before we go into how we then build this system we need to introduce this concept. So internally we use something called a manifest. And conceptually, it's just a signed list of all the records and a checksum within a fixed time period. So basically it says from 1 p.m. to 2 p.m., this is all the records that we expect to be written in the system. And a checksum, so if you change anything, we would be able to detect it. In Legistar itself, a manifest is actually just a digest, an account of the number of records, and then the time order index becomes the list of elements. But from the digest and the count, we can then know whether the index is correct as well. Great. So how do we then know whether something is correct? So we chose for this three-way verification approach. So if you just have two tables, and you do a validation, you see there's something not right. What is the correct value? Is it what is in the record table, or what in the index table? You wouldn't be able to know. So we wanted this third item that can kind of tell us if any of these things are drifting from each other. And this is where we're using manifest. So we have this concept of a manifest builder. And for this, we're using Amazon DynamoDB streams. I'm going to talk a little bit more about streams in a moment, but basically what this is, that streams allows us to have this isolation layer, this air gap basically, between Legistar itself, the thing that writes the data, and when something then written to DynamoDB. So from the stream, we can see what is being accepted or committed to DynamoDB, and we can see exactly what was the data that was actually being written. So from this, we can now generate a table of manifest that basically says this is the digest, this is the count, and we have this air gap, meaning that even if there's a bug in Legistar where it didn't write the index, whatever, we'll be able to see in the record that, because it's DynamoDB that's providing the stream independently, that it actually was written to the record table. So, what we then do is we can then now verify these tables internally, and we can actually see that we are correct when the system is running. What we do mostly is we validate time index and manifest, because we can do that live, because it's a very fast thing to do. The record and time index verification is slightly trickier because it actually requires a scan of the record table. But we do that periodically to kind of make sure things are in order. But having it on the manifest and the time index means we can actually have very short iterations of where we're able to detect if there's a problem with the system. So this is for one region, but we also want multi-region. So in that model, where we're actually running the manifest builders in both regions independent of each other. And when you then throw in replication, that means when the record is being replicated to the secondary region, our DynamoDB streams will be created in both. We create a manifest. If they match, we know that the same data has been replicated to the secondary region. And by actually then comparing the manifest across the regions, we can now say, okay, everything is actually consistent when we also compare it with the time index. So even if the time index, for example, is delayed in its replication, we'd actually be able to wait with saying now it's closed up to this point because we're waiting for the index to be replicated. So that means when we can say that the manifests are identical in these two regions, we know that exact same data is there, even though it's independent tables and replication is independent. So that's how we do internal consistency checks. So now I'm going to go a little bit into the manifest builder, which is kind of the component that enables this. So what the manifest builder does is basically it takes a stream of events, and basically it's time, and it breaks it into these gapless, non-overlapping time intervals, usually half an hour or something like that. And for each one of these, it calculates the manifest with its account and a digest. So we can say exactly what was written in this time period is this number of record and this the checksum of them. And from this, we'll basically be able to compare the verification as I showed before. So all this is based on DynamoDB streams, and I'm just going to quickly run through what DynamoDB streams is to kind of understand how we build the manifest builder, which turned out was actually quite a challenge to make this work at scale and correctly. So a DynamoDB stream is basically just a queue. You can see it as it's a queue of events that says, now I wrote this particular item, and yeah, that's basically it. So when an item is inserted, it's being inserted into the queue, and then I can read it. And DynamoDB streams has this nice property that it's ordered, and it's exactly once, meaning that when I commit an item into the records table, it shows up exactly once in this queue. And this basically continues. But obviously, it's not as simple as that because it's not just one queue. Because this system has to scale and handle these 100 millions of writes a day, it's actually multiple queues underneath. So when I write a record, it's actually being sharded out between these different shards, and you still have the property that an event is only in one shard, so you can't have duplicates in between these shards. But obviously, it gets a little bit more complicated than that because shards in DynamoDB streams are not just a continuous queue, it is actually these time-limited shards. So at any point in time, a shard can close and a child is created. And now we kind of have to keep track of, okay, is this parent shard closed, and is this does this child shard exist, and does it have data, and so on. So this obviously begs the question is, how do you actually consume this in some kind of efficient way, so you know that not only that you're only processing every shard once, and only one worker is doing, but also that you're processing all the shards. What if you lost one of those? Then our whole system kind of breaks down because we need to make sure we're capturing everything. So that's kind of the problem. And then when you don't throw in multiple workers, now it's even harder because how do you distribute the work between these, which is typically known as lease management. But luckily, DynamoDB has our back here, so they basically have Kinesis. So this is not Kinesis, the service, as you know it. It's a client-side library that has an adapter for DynamoDB. And internally, it manages all this shard orchestration. It makes sure to handle leases between different workers, and it makes sure you're processing everything. So it knows about the full structure of how these shards are laid out. So that's the first thing that we basically use DynamoDB Kinesis to kind of consume this, and we can scale it out. The second challenge we kind of had is how to do exactly once processing. So although the stream provides exactly once guarantees that an event is only there once, how do we actually make sure we consume it only once? Because what happens in Kinesis is that you checkpoint and offset, similar to what you do in Kafka if anyone worked with that, and I go and read from a particular offset, and I start reading stuff. And this is basically what the worker does. So it reads offset 1, it writes to the manifest, and says this is the digest, and then it takes the next one, and everything is good. But what happens now if the worker dies? And it didn't know that it actually finished processing event 2 in this case. Because what happens in Kinesis is the checkpointing of the offset is different from actually a separate table compared to actually when we're writing to the manifest. So this is a bit of a problem because when the worker now starts up again, the last checkpoint was 1. Should it then process 1, or what should it do here? Because we already updated the digest, which takes what the data was in event 1. So now what we actually would be creating would be wrong. So what we actually did instead is we're keeping track of the sequence numbers. So every time we update the manifest, we also say this is the digest up until this sequence number. Because streams has a nice property is that every event has a one-tonic increase in sequence number, so you can actually use that to achieve this exactly once processing. So now everything is happy that you update the sequence number, and then you write it again, you set the sequence number again, and this process kind of continues. Obviously, this is a simplified version. This runs in parallel. There's batching and all kinds of stuff, just to kind of illustrate the purpose. So this approach kind of led us to the first attempt we did in building this manifest builder, which is basically this. You have a manifest, you're consuming these 3 shards, and whenever you're moving forward, you update the digest and the sequence number, and then we use optimistic locking in DynamoDB, again with the conditional expression, to kind of make sure when there's multiple workers running at the same time that they're not kind of overriding each other. So the optimistic locking, in case you don't know, is just you read it out, you make the change, you write it back in, and you say, I expect this particular version, which is very easy to build in DynamoDB. But as the system scales, that's where we kind of hit problems with this attempt. So with 3 shards, it's fine, but as our table kind of grows, now there's 5 shards, and even more shards, and even more shards. And you can kind of see where I'm going with this. At some point, this is just going to be way too much data to store on a single item, and we cannot use this optimistic locking to kind of make sure we have this transactional committing of sequence and digest. So at this point, we kind of hit a hard limit saying that, okay, we can't scale this because there's just too many shards when our table grows as it does. So that led us to the second attempt. In the second attempt, we basically divided into 2 different tables. So we have a manifest table as before, and we have a chunks table. And a chunk in this case is just for a single shard. We say what is the digest, sequence number, and we have optimistic locking on that particular chunk. So now, when we add more shards, we just basically scale out this particular table, and that uses the normal scaling out of a DynamoDB table. So that basically infinite scale here. When that is done, we process everything. We can then merge them into a manifest by merging all these digests, and we get a final manifest of what we need. And then we can go and delete these chunks. And everyone is kind of happy. This approach has served us well. It's running in production and handling our load without any problems. But it took a few attempts to kind of get there. So we've seen, we're doing completeness and consistent indexing and verification and all this stuff. So you might ask, was all this work actually needed? Can't we just trust that whatever we put in DynamoDB is there and our system works, and because we have all the unit tests and we have the integration tests and best practice and code reviews and all the stuff that is common for building software. So why is all this needed? Because the system is correct, right? All our designs are good and implementation should be good because there's tests and yeah. But it turns out that even if you're doing your very best, there's still going to be bugs in your system because, well, bugs are going to be there, as any developer knows. So from with this system, we actually caught multiple bugs in the system. We caught a bug in our indexing that, for some reason, didn't insert the right index. We caught bugs in our offloading. We caught bugs in Spark itself, that where it actually silently drops data without anyone knowing. We caught bugs in the manifest builder where it drops a shard and it calculated the sequence number wrong and so on. There can be bugs in the replication because there can be replication delay we didn't expect. In our query layer, there could be bugs in how it actually reads things out. It could drop something, and we found bugs there as well. And even in the verification itself, the things that are supposed to show whether things are correct, we found bugs. So basically what we're getting to here is that there can be bugs anywhere in the system. And kind of the conclusion of all our work here, which it's not just for DynamoDB, it's also for any kind of other database. We're also building database internally at Uber where we're seeing the same kind of thing. If you're building a system where you have multiple components, bugs are going to be there. Not only code bugs, but also where you have a wrong assumption about a system work or something like that. So the conclusion in all this is your data is not valid until you have validated it. And we've seen this again and again across multiple systems. You have to validate your data to know whether it's actually correct. And that kind of leads to the corollary of is, if you haven't validated your data is most likely invalid. So that's kind of our takeaway from building the system is, you have to validate your data because bugs are going to be there, even if you have the very best attention. And yes, that is basically what I have for you. So I'm going to take questions on the stage afterwards if anyone is interested. And with that, I'm just going to say, oh yes, please remember to complete the session survey in the app when you're done. Thank you.